Hello guys, so we were solving neat code sheet. So we were on try section, and yesterday in our previous video we have implemented a try data structure. We have written code for a try data structure. That try data structure act as a dictionary to store strings, and we can efficiently search the string in this data structure and store the strings. So now we will continue this section with the next question. So next question is design, add and search words data structure. Okay, so whenever we see we need to add a string or we need to search a string efficiently, we should on the first go should think of a try data structure. So let's read out the problem. So the design a data structure that supports adding new words and finding if a string matches any previously added string. Okay, implement the word dictionary class. Word dictionary initializes the object. Okay, so we have first function add word function. This function adds a word to the data structure. It can be matched letter. So this will use to add the word in the data structure. Means we will be adding a word to our try data structure. And the other function is search function, returns true if any string in the data structure that matches word, or false otherwise. Word may contain dots where dot can be matched with any letter. Okay, so let's see, we have one variation here. In the search part we have our search word. Means here this word is a search word dot ad. So in search our word can contain a dot where dot can be matched with any other letter. Okay, so we can match this dot to any other letter. Means we can replace it with any other letter and further look for this a or d. So I think we should try to match this dot with every uh, every character a to z, and wherever it matches we can initiate our call search function from there itself. Okay, so first let's initialize our try data structure. So we will create a class, public class try node, and in this class we will create an array of try node children. So I think we only can have lowercase English letters while adding, and search can contain dot, but while adding a word it will only consist lowercase letters. So TRIE. So we will create try node of 26 letters, and we will have a value. We can also call it as a boolean word end. This will indicate a word is ended. So in our constructor try node we will initialize this word and as false, that our word is not ended for a default case. So this is our try data structure. So we can call it as a try node. So now we need to whenever our word dictionary class is initialized, this constructor will be called. So we will initialize it as a we will use a head variable to create a node, and whenever our word dictionary class will be created we will be initializing this head to new try node. So this will be head of our try node. Okay, so while adding a word, what we will gonna do, we will going to iterate this word, and our current character will be, I think this will work. So current character will be word dot character at position I. So this is our current character. So we need to put it into our this try. This is basically our try. So we can also call it as try. So this is our try. So we will initialize a reference variable, temporary reference variable to our try. And if our this temporary variables children, we will access these children, and it's this index. If this is null, that means the character is not added, so we will add this character. Simply we will add a new try node, means this node, means this object will indicate that this character is present, means character at this position is present. And then we will move our temp to temp dot children character minus a. And when our word ends, then what we will do, we will mark our that node will be marked as the word end, so we will mark it as true. So this is how we insert a word into try node. We similarly implemented this function yesterday, where we uses this word add and as a integer value, where we have put a -1 instead of true. So boolean, using boolean will be uh, more handy. Now we need to search a word. So yesterday also we have implemented search. Let me show you that part. So this was our insert function, which is same as we have implemented today. And in the search function we simply, like we have inserted in the similar way, where we have iterated the our try and checked whether object at all the character positions is present or not. But in current question which we are solving, our search word can have dots, means in place of dot we can use any word at a current position. So we need to, we can have then multiple choices. So it gives us a kind of vibe of using DFS, that we need to iterate all the ways whenever where we hit a dot. So we need to iterate all the children values, and for every value we need to give it a try. So let's call a DFS function. So let's pass word in DFS function. We will not need to pass this try, because this is a this try is a global variable, so in our class. So we will pass a word. What else we can pass? We can pass current reference, and we can pass the current reference at which we are currently. So let's initialize a temporary node. So initially we are this is a head, basically tries. So initially we are at this position. So let's initialize our DFS function. It will return a boolean and take a string word as input, and try node temp as the reference to our try node, current try node. I think we also need to pass the current position in our word, means the position at which we are index, means how many characters we have found. So initially we have found 0 characters, so we can put a index also. So let's say whenever our index reaches becomes greater than or equal to word dot length, then we can say we have iterated all the uh, characters in our word. And if our temporary variables word end is true, then we can say that it is a word, it is a valid word, so we can return true. Otherwise we can return false. So instead of doing this, we can return temp dot word end. Okay. So we can have two options. First option is, if our word dot character at index position is a dot, then we need to take another approach. Otherwise it will not, it will be a character between A to Z. So in this case we need to compare it, means we need to check if our temp dot children let's initialize our character here itself. So if our character is dot, then we need to replace the dot with every character. Otherwise we will check the children at this position and see if it's null. If it's null, then that means the word is not present, so we can return false. Let's say if it's not null, in that case we need to call our DFS function, and in that DFS function we need to pass our word. We need to increment the index that we have found the character at this position, and we need to move our temp to temp dot children and ch minus a. If this returns as true, then we can return true. Otherwise at the end we will return false. Okay, so in the case of dot, what we will do, we will iterate from character A to character Z, and check if we will check this thing only. So I think we can make this code shorter. So first we will see if this approach is working or not. What we are doing here, we are iterating A to Z, and we are checking for every position if that word is not null, and we will try that word. If that returns true, we will return true. So let's see if this works. Hmm. So this is our if statement, this is our else statement. Else without if. Okay, we have a return, we don't have a ending statement for this if. Okay, we have taken it as a head. It should be try here. Okay, instead of I, this should be idx. Okay, our first case is working. Let's try to submit this. Okay, our approach is working and it's 90% faster. So I think it was our first submission for this question. Okay, so let's see if we can, as we are using this condition repeatedly, can we means do it in fewer lines. Hmm. Okay, we are reusing this condition. Means in the case of dot, we will replacing dot with every character, and then we are checking if value at that character is not null. If it's not null, that means this is present in try, and we are calling DFS. If that DFS returns us true, we are returning true. Let's say we have a character array. Characters, new character, and we put it A, B, C, D, E, F, G, H, I, J, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, and Z. So if our character is not dot, in that case what we will do, we will replace our this array with this. We will extract this, remove this, and what we will do, for current character we will iterate our chars array. Let's make this global variable. Let's run this. Okay, we as its final variable we cannot change its value, so we will, okay, I think you are having some issue. Why this is happening? If it's not dot, then in that case we are doing this. A B C D E F G H I J K L M N O P Q R S T U V W X Y Z. Okay. What we were previously doing. We are having a character, and if that character is dot, in that case we were moving from A to Z and calling our this function. So we have put up our A to Z here, and if our character is not dot, which means this condition, in that case we will only put ch in that. We will replace our array with this variable, and we will pass our current. Otherwise it will, in the case of dot, that will remain this itself. So where's the issue is coming? Let's see. The two versions of achieve the same functionality. However, there is a difference in performance, memory usage, and clarity between the two implementation. First implementation, second implementation. It's less clear. The first implementation is preferable for both clarity and performance, especially in the case where non-wildcard characters are more frequent than wildcards. If wildcard are expected to dominate and you want to reuse structure, the second can be considered, but introduces unnecessary complexity. So this introduces unnecessary complexity. But we these are not giving same output. That was our issue. According to GPT, they should give same answer. Let's leave it. I think it's not a better approach also. Means our this approach is better as compared to what we were trying to implement. Let's see if GPT can make this approach better. Okay, it's the pretty same solution. So I think we are done with this solution. So its time complexity of heading word is length of word, and space complexity is 26 into L for creating new node for each character, and time complexity for search is L, where L is the length of the word. For wildcard searches, in the worst case, it is 26 raised to the power m, where m is the number of the wildcard. Okay. So tomorrow we will do word search too. Okay. Thank you.